This animation shows what happens when you write CSS through rote memorization and trial and error. You plug in properties, hope they work, and inevitably end up with a chaotic, unmaintainable codebase where fixing one layout breaks three others. To stop guessing, you have to look past the syntax and understand the deterministic mathematical engine the browser actually uses to parse and apply your styles. Welcome to this Royal Research Masterclass. Today, we are reverse engineering the CSS parsing engine. We will break down the mechanics of the CSS engine, the geometry of the box model, the mathematical conflict resolution of specificity, and the execution sequence of the Cascade. Transitioning from a memorizer to an architect means trading the frustration of trial and error for total, predictable control over any web layout. We begin with this diagram illustrating the core rule of web geometry. The browser treats every single HTML element as a hierarchical rectangular box. At the center is the content layer, the innermost core where your actual data lives. Surrounding that is the padding layer. Padding provides the internal breathing room that physically pushes the outer edges away from the core content. Next is the border layer. This forms a hard, defined edge, securely locking it in. Finally, we have the margin layer. Margin acts as an invisible external force field that dictates exactly how far away neighboring elements must stay from your border. Layout bugs are rarely random software glitches. They are almost always a failure by the developer to account for how these four physical layers compound onto one another. Here is the dangerous default math of CSS. When you set a specific width on an element, the browser only applies that width measurement to the innermost content layer. This animation shows the immediate consequence. Adding padding or borders to that element physically inflates its total size well beyond your declared width, easily shattering precise grid layouts. The standard architectural fix for this is declaring a property called box sizing border box. Watch the right side of the diagram. This declaration forces the browser to absorb padding and borders inward, ensuring the element remains locked strictly to its declared total width while compressing the inner content to make room. Standardizing this specific calculation across your entire document is the mandatory first step for making any complex layout responsive across varying screen sizes. Once your geometry is stable, you face the problem of scale. When hundreds of style rules target the exact same element, the browser needs a deterministic way to pick a winner. The browser resolves these overlaps using specificity, a four-tier mathematical weighting system. This scoreboard visualizes the calculation. The lowest tier of power belongs to broad element selectors and pseudo-elements. A pseudo-element is a keyword added to a selector that lets you style a specific subpart of an element, like its first letter. The second, much stronger tier belongs to classes, attributes, and pseudo-classes. A pseudo-class is a keyword that targets an element's state, like when a user hovers over it with their mouse. The third, highly rigid tier is reserved for ID selectors, and the ultimate overriding tier is triggered by inline styles. Inline styles are CSS declarations written directly inside the raw HTML tags, rather than in a separate style sheet. The browser simply calculates the highest score. Whoever brings the heaviest math dictates the final color, size, and shape of the element on screen. The counting mechanism is literal. If two competing rules both use classes, the browser simply counts how many classes are chained together in each rule to break the tie. This is why you should avoid using IDs for styling. Their massive specificity score makes them incredibly difficult to override without writing increasingly convoluted code. Instead, prioritize flat, simple class structures. This keeps your specificity scores low, maintaining a flexible architecture. You must also avoid the .important declaration. The .important rule is a CSS declaration that overrides any other conflicting styles, acting as a brute force hack that short-circuits the entire mathematical scoring system. Managing specificity is essentially managing predictability. Low scores allow a codebase to scale cleanly, while high scores cause permanent styling gridlock. The final architectural pillar is the Cascade. This diagram illustrates the Cascade as the master algorithm, a final sequence of four logic gates that processes origin, importance, and specificity to actually paint pixels on your screen. Gate 1 checks origin. Every browser has invisible default styles, called user agent styles, which provide basic formatting for raw HTML. Your written author styles must actively overwrite these defaults at this first gate. Gate 2 checks importance. Any rule carrying that dangerous important flag immediately bypasses the remaining logic gates and forces its way through the entire funnel. Gate 3 checks specificity. All surviving standard rules are subjected to the strict mathematical scoreboard check we established earlier. The term cascading style sheets literally describes this downward flow of data, where only the strongest rules survive the filtering process to become visible layout. But what happens when two competing rules have the exact same origin, importance, and specificity score? In this diagram of Gate 4, we see source order. In the event of a perfect tie, the browser simply picks the rule that was written last in the actual code document. To manage this at an enterprise scale, developers utilize CSS preprocessors like SAS or LESS. A CSS preprocessor is a program that lets you generate standard CSS from a unique syntax, adding features like variables and logical nesting. These tools allow developers to group and intelligently sequence their code blocks so that the source order gate works in their favor, smoothly applying baseline styles before complex component overrides. Mastering the cascade means you never have to guess why a style didn't apply. You simply trace the rule back up to find the bottleneck. This wireframe demonstrates the interconnected engine. The box model provides physical geometry, specificity provides conflict math, and the cascade provides the execution order. A senior developer understands this underlying architecture, replacing visual guesswork with an exact calculation of math and logic. Open your browser's developer tools today, inspect your current projects, and actively hunt down physical layers, the weighting scores, and algorithmic gates. Once this foundational logic is rock solid, you are truly ready to construct complex, advanced architectural systems like CSS Grid and Flexbox. Thank you for completing this Royal Research Masterclass. Remember, true design innovation doesn't come from breaking the rules. It requires a master's understanding of how to use them.